All right, so this is going to be a solution video for problems A through C. And yeah, this is sort of a late upload because the round ended like 2 days ago. But yeah, I didn't do well in this contest, and I'm not too surprised because I've been like, as you can see from the January to March area, like I was actually like practicing coding, and then from like April to like now, like probably like the last 8 months, I haven't done jack in problem solving, and so my skills have like considerably fell off a lot, which is not too surprising, I guess. Like, cause over here from January to March, I peaked at like 1483. Like, I was actually getting better, and then I just stopped because like stuff happened and like I had other stuff to do. Actually, probably not. Probably I just didn't do coding. Like, Codeforces, like I just didn't do it. So yeah, my rating is like a lot worse. I'm like 200 points above below my maximum rating. Yeah, but I'm not really embarrassed to say that. It doesn't really matter to me. It does matter to me, but like I'm obviously not gonna kill myself over it. So let's just get better. So let's do the first problem, which is problem A, which is set. And so okay, so in this question, we're given a set of integers from L to R, which means that we have every integer between L and R, right? And we're also given an integer k. The idea is that we want to calculate the maximum amount of removals in this set, and there's a condition, right? The condition is that like in order to remove um, a number like x, it must have at least k multiples, including itself. So all this like means is like the kth multiple. All this condition literally means is that like first it means that well x number from the set. So first that means that like this is true since it's from the set, and it also means that like this condition such that there's at least k multiples of x in the set. That means the kth multiple is in the set. Like this is what this condition means. And so actually there's like then you can actually notice that like you can only remove x if it actually satisfies this inequality. So we know that like kx is a more restrictive upper bounding on r because like kx is obviously bigger than x. So if kx is bigger than x, then x is going to have to be smaller, like as a result of like this like well we know that this is just means like ax is this is like r over k, and the reason why it's floor is because like you don't care what happened, what's the decimal after it because x is an integer. So that's what this condition is, and like the idea is that like well this bound, this upper bound is more restricted than this upper bound. So really, the first condition is just saying that you can only remove a number if x is in between this. But there's a very important assumption. So you might just for the sake of rigor, the very important assumption is that like let's just say like you're removing like a set of numbers. Let's say you're removing a subset of numbers in the set of S, right? The idea is that like you remove them in ascending order because you want to make sure that like if you remove some number, I don't want to remove like for example, I always remove them in ascending order because let's say I don't, right? Let's say let's say I remove x and then y, but x is greater than y. Then it could be that x is some multiple of y. And if x is a multiple of y, then I reduce the amount of multiples of y by one, and it might fill the condition that has at least k multiples. So to just make sure that like each removal is independent from each other, you always remove in ascending order because obviously removing like the previous number that you removed cannot affect the current number because the previous number is not going to be a multiple of the current number because it's smaller. So that's just the assumption that you have. And so now if you know that each removal is independent from each other, then the question is just like, does it have at least k multiples of x and s? It will have at least k multiples of x and s because that's what this condition over here means. It means that like if removing x from the set, x is between L and R, and its kth multiple, and it has at least k multiples, that means its kth multiples less than or equal to R, then the idea is that like x is less than or equal to R over k, and then um, since all removals are, we prove that all removals can be independent from each other, then we can just literally do our answer is R over k minus L plus 1. Yeah. So there's two tricks here in this question. The first trick is to understand that removals can be independent from each other, um, because we don't want other removals to negatively affect other removals. So we can just assume that they're independent from each other if we remove these numbers in ascending order. And then the second observation is really just noticing that maybe the first or second observation is really just noting that the first one is just like a bunch of math. It's just basically an inequality, right? That's what it's saying. Um, and it's basically saying if you remove a number such that it satisfies like inequality, you can remove it. So that's pretty much it. So then the solution here is just the code is pretty simple. Just well, I did some nonsense because like it might be weird. You might have like a negative number and stuff, which might be a little bit annoying. So just like max it with zero. It might be some extraneous thing, like maybe just like k is like too big or something. So if k is like too big, then you have like a nonsense. It's hard to like have that many multiples, right? So let's do this one. B. So yeah, this one for some reason like I was struggling, but it's really just like an observation again. So it's like you have a binary string s of length n, and ours gives you another binary string of length of n minus 1. And we're playing a game here. We're going to perform n minus 1 operations in order from I to n minus 1. And the idea here is that, like, basically, if you have, like, some binary strings, so I'll just, like, use a test case to show this. Let's use this one. Then the idea is, like, these are, okay, so this is, like, your operation. This is your, I'll probably just do, probably just easier to edit. So this is, like, your S, and this is your R. And the idea here is that like you do operations, you go through R and you do operations, and basically one tells you that like find some consecutive pair of bits. So by consecutive, I mean like adjacent bits that differ, and if they do differ, replace it by one. And like really this question just is the hard part about this question is like what do you do when there's multiple consecutive pairs of bits that differ? Like does it really matter? Like, can you replace them? Um, so yeah, that's been the question. Is sort of like a little bit like, but you're this is like sort of a bad mindset because you're sort of like thinking about like simulating it ish. Like when you're like thinking about, oh, well, which one do I replace? Does it really matter? Like that's not really what the entire solution is. Really, it's supposed to notice that like again, these conditions need to be reduced. Just like in the other one, if you notice in problem A, like we had to reduce like what these operations are. Like usually they'll give you like some sort of operation that can really just be that like there's some like redundancy or like there's just a way there's a nicer way a variant or like so there's a nicer way of saying the operation that makes the question clearer. And what I mean by this is that like basically they're saying that like if you can't find consecutive pairs of bits that differ, then you lose. So the idea is that like if the string is all ones or all zeros, then you lose. So the idea is that like as long as the string has like, at least one one and at least one zero, you're chilling. So the idea is that like instead of worrying about the string as like some order of like ones and zeros, think about it as like how many ones do you have and how many zeros do you have, right? Because then an operation is really just like saying if I'm replacing one with some consecutive pair of bits that differ, then I'm just decreasing the amount of zeros in my string by one. And symmetrically, the same argument applies for zero. If I replace some consecutive pair of bits um, with zero, then I'm effectively taking a one and kicking it out. So I'm decreasing the amount of ones in my string by one. So then that's basically what it is. It doesn't matter where you choose them. The idea is that the same thing is going to apply. The same frequency is going to reduce, like in the same way. It doesn't matter if I choose 0, 1 or this 0, 1, the idea is that like when I do the first operation, um, the zeros will decrease by 1 because ultimately that's what you care about. You care about, do I have at least 1, 1 or do I have at least 1, 0? Like what are my frequencies? That's all I care about. And as long as that condition is met, then you know that like you can continue. So basically the impossibility case, like this basically means that like, do we have at least 1, 1 and do we have at least 1, 0? That's what it is. As long as that condition is, as if you can know that that condition is met, if that condition is met, then obviously you're chilling. So I guess like the observation here is like, yeah, it's sort of like it's like more of like, if you don't see this, you don't get the problem. But I guess it's like not too bad, but I don't know. I didn't see it. But I guess like it's sort of like always looking for like a different way to say things that make it easier. But it's like easy to say that in hindsight, but it's just like, yeah, if you can't find consecutive pairs of it, like as long as the string has at least 1, 0, 1, 0, 1, 1 and 1, 0, then like this condition is true. So the impossibility case is really just gonna be simple. It's just like simpler. So I guess that's what it is. Yeah, it's like constructive. It's yeah, whatever. So yeah, this is like the solution. Um, Basically, all you do is you count the number of zeros and ones in initially, and then for each iteration, right? You first want to check like, do I have at least 1, 0 and at least 1, 1, right? I'm checking the impossibility case, and if either one of them are 0, like I know that I'm bad. Like it literally tells me to stop. Like I'm just simulating it, right? And then I apply my operation, right? If it's a 0, decrease 1 by 1 because I'm just kicking out the 1. And if it's a 1, then decrease zeros because I'm just kicking out a 0. And then I'm just gonna like go through each iteration. That the impossibility check is, we said that like it reduces down to this. Is there an yeah? That's what it is. So yeah, I guess it's just like simplifying that condition, and then you're good. So for C, there is actually two ways to do this. The first way is DP, and the second way is binary search. And the first way is probably just more standard and like simpler to think of, like more probable. It's more probable that you think of. The second one is like kind of like more unique and like kind of like you probably wouldn't think about it. Like less people probably thought of it, but basically this is it. I mean, the problem statement is simply proposed. It's just saying that like you have some contests, and your performance is indicated by the value of like your performance on the ith contest is indicated by the value. So like I said by, and like the idea is that like if you perform better than your current rating, then of course you go up, right? And you go up by 1. If you perform the same as your current rating, then nothing happens. And if you perform worse than your current rating, then you lose rating. So then the idea is that like if we have to remove some contiguous or like some continuous set of contests, so some interval LNR, then what is my maximum rating? I'm assuming that I have to remove some interval, and it cannot be an empty interval. It has to be at least size 1. So yeah, if you first think about it, this does smell like DP ish, because like the idea is that like it's sort of hard to like. You first have to understand that like when I was thinking about it, I was like, oh, okay, maybe I can like fix some L. So this is why like you sort of just like kind of think it's just DP, because like I was trying to say like maybe I can fix some L, right? And if I fix some L, and then that's like where I want I was basically trying to say like for each L, can I find like the best R to pair it up with, and just like calculate like maybe like find like the interval, like actually find the interval. So like for example, maybe fix the L for my interval, and then find some R. What that means is like to find the best R, it's very dependent. Like it's super dependent on like what this X is. Like it's really weird. You know that like this prefix, right? This prefix like when you do contests from 1 to L minus 1, you have some rating, let's say it's X after doing it. Like where you can place this R is dependent on that prefix. Like where this R is dependent on the prefix. So it's like you can't even like compute like something with a suffix. Like maybe you can say like like because this question is like out of the suffixes, like can I like which suffix would be better, like pairing it with X, like you know what I'm saying? But it's like very, very, very weird. Like this is just a weird question. So it's like deep, like if you just think about it, like because every suffix is like dependent on a prefix, there's no way you can do them independently. Like you can't pre-compute um like things for a prefix and things for a suffix because they're independent from each other, because they're dependent on like the suffix is dependent on the prefix. Like the fact that I have X, or like the fact that like yeah, I don't know like which suffix to choose because I don't know like what, like this varies all the time, then I like that just means like they're dependent on each other. So really just like that doesn't work. So what is an interesting question to ask yourself is like, what is the maximum possible rating if I only care about the first I elements? And the reason for this is because this technique allows you to say that like if I only care about the first I elements, I can always assume that like I know the maximum rating after the first I minus one contest, and the question just reduces down to like, let me add a contest and just see like, what is the effect of it if I just add a contest? So it's basically like saying like I've already done like most of the work. Now I'm just gonna add a contest and see like, okay, can that really change anything? That's what it is. Can that really change anything? So this is like a very standard technique is like assuming you know given that I only so basically solve the question with the assumption that you did it for I minus one, I minus two, all the way down to one. So it's not too bad. So the idea is that like the idea is this, right? If I already have it for the first I elements, right? And I append some new guy. Or I might let me see, let me do I minus one. Let me yeah. So if I already have it for the first I minus one elements, like I know the maximum rating after the first I minus one elements. Because obviously, like when you're on, when you want to if you when you want to maximize like the maximum rating after eye contest, it's the assumption is that like obviously you maximized it for the first I minus one contest, like obviously. Um, so the idea is that like yeah, I can basically just say well um. Actually, I think a better way to explain this is saying that like on contest I, you know that if you want to maximize the possible rating after I contest, you obviously need to maximize the possible rating after I minus one contest. Like I think that's a more natural way of explaining it, of why you would use like DP on a prefix, because it's like is this idea that like well obviously if I'm trying to like solve this problem on the first I contest, or like find the maximum possible rating on contest after like the first I contest, then the idea is that like well I need to know the maximum possible rating on the first I minus one contest. So I let DP of I be like the maximum possible rating on after contest for if you given that we only care about elements from 1 to I, and that makes sense. So the idea is that like I already have a DP of I minus 1. I already know how to maximize the first I minus 1 contest. I already have my maximum rating for that one. So the question is, given that's true, given that I know like the maximum answer, then how do I find it for I plus 1? So the question is like when you're penning a new element, right? A new or sorry, I when you're penning a new contest, like does the contest matter or not? Like it either matters or it doesn't. In the sense, like if you were to skip this contest, right? If I were to skip this contest, so that means maybe the interval ends on I, then it didn't matter. Like the answer to the question, like this is like if I were to skip this contest, then it didn't matter, right? Because like my answer is just whatever DPI minus one is. I don't care. I skipped the contest, so I'm just maximizing my rating after. If I skip the contest, it's like I don't care. I don't care about it. And you have to actually observe. But then the question is like, you realize that like this. So this is like the tricky realization. So I mean, sure, you have some base case like DP of one. Since you have to skip a contest, you know that like you'll have a rating of zero. But if you just like start plugging that in, like you're just gonna have the entire rate to be zero. So it's like, wait, what? So it's actually weird. So instead of like thinking about that, really, if the ith contest matters, we need like some casework, right? If I choose to skip the ith contest, so let me represent that with by adding another state, which is like skip. And if I choose to skip the contest, then you actually can notice that like the optimal answer is just some prefix maximum of like the answer. Like prefix maximum as in like if we were just to do the first I contest normally without any skipping, like over all those prefixes, what's the answer? Because I know that like I know that my interval is going to end on I if I skip it. So if I skip the thing, then like basically just from prefixes from one to I minus one, what is my maximum answer? So I basically know that like, you know, at least the DPI one, um I know that like DPI one, like that is just like or whatever. But I basically know that like in that case, the array, because there's like two arrays, rather like, yeah, there's two arrays. But in that array, like for my DP in that case, like it's just basically just prefix maximums. So I can just populate it like that. It's interesting that like you can't just like assume DPI is like DPI minus one. Oh no, but like well yeah. So but you notice that like this doesn't work because like you sort of need another state to describe it. But this isn't a skip case, right? This isn't a skip case. So now like that's like if the ith element like didn't matter. Like if it didn't matter, then like this question just boils down to like can you find the maximum prefix from one I minus one if you just simulate it normally? But then so like and this is represented by this case if I skipped it. But then like the element might have mattered. Like if I append the element, it might have mattered. So if it mattered, that means I'm taking the contest like on I. So like if I take the contest on I, so this means like it did matter. Then the interval lies somewhere here. So let's say so to represent me like taking the contest, I'm saying I didn't skip I. So if I didn't skip I, then the idea here is that like if I chose not to skip I, then the idea is that like well this is the same thing as saying like this is the same thing as saying like well what if I just like did DP of me the interval either ends on I minus one or it doesn't. Either I like that you know what I'm saying? So it's either this or DP And then you can compare this with like the new contest, like contest A sub I, to see if you have to add one or not. But the idea is that like for example, if you didn't take the ith contest, then you know that like the maximum rating in the first I-1 contest, like either the interval ends on I-1 or it's just some interval there. You can just like compare it with A sub I. Like for example, if A sub I is like greater than this guy, then you know you performed better, so then you can add one. And then it sort of just like depends. Oh, this should be one. My bad. It sort of depends, but then that means you can find what this is. So I'll show you the code that will make more sense. But the idea is that like the general outline is like if I just think of like finding the maximum rating after the first I contest, then when I append I, right, it's like it either matters or it doesn't. If it did matter, then that means I did not skip it. But which is basically just saying that like, well, you realize that you need another state because it's like for the skip case, because like if it didn't matter, like if I skipped it, then like it's just like some prefix. But if I didn't skip it, so maybe zero, right? That case, like there's two different cases, right? Like it mattered or it didn't. Then I know that like I can basically just say the interval ends on I-1 or it doesn't, and then use those cases um, to come up with my best answer. Yeah. So the solution will look something like this. So it's either like yeah, it's pretty simple. So ith prefix and did the interval end on I. So actually, instead of saying like did it matter or not, it's more precise to just say did the interval I choose end on I. And the reason, so this is sort of motivated by the sense by saying like you're thinking about like when I append the ith element, does it actually affect previous states? Like, does this actually matter? Like it's only one element, so can I just take the same answer or can I not? So you sort of split it in cases, right? Where it did matter, where it didn't matter, and you realize that like if it does matter, then you know the state is just like it's more precise to say that like the interval you chose ended on I, and if it did matter, right, it ended on I-1 or something else. So if I want to just like find my answer, like for example, if the interval always ended on I, then it's just me finding the prefix maximum. That's what it is, the prefix maximum. So to get my previous state, I just take this guy and I find my rating. Yeah, I find my rating from the previous contest, like the rating that I'm entering in. Yeah, because I represent the prefix maximum. Cool. So that's for that case, and then for the case of like the interval not ending on I, if the interval doesn't end on I, then the idea is that like, well, I need to see like how can I get my highest rating from the first time I-1 contest. So if the interval doesn't end on I, then like, well, it obviously ends on I-1 or not, or something beyond that. So I can basically just use the I-1 state and basically get like all the possible things from ending on I-1 and then not ending on I-1. And then I can just calculate the new rating if I like append a sub I and in each one of those cases, and then you know take the maximum among those. And then either the last question is like last thing you need to do is like either you can like end on either the interval ends on the last element or it doesn't, and then just take the maximum of them. And then like you have to be careful because the base case. Oh yeah, always think about the base case first. Like you always have to like choose some interval to skip. Like you always have to. So if I always have to choose some interval to skip, then the idea is that like the DP of one, so DP of like the interval ends on me, like of course at zero, but also DP of 1 0, like the interval doesn't end on me, that's still zero because like you have to skip. So that case would have to be zero. So you have to like you represent it by that. You represent like you having to skip by like DP 1 0. Like yeah. So yeah, that's you have to be a little careful there. But other than that, it works. So Yeah, it's a little annoying. Okay, so then there's another solution, which is a binary search solution, which is like honestly, like it took me a while to understand a little part of it, which was really annoying for me. But then like I just realized that it's not that bad. So in this question, so you can do the same thing. So first it says like, what's the maximum rating after the recalculation if he chooses the interval from model R? So maybe you can ask yourself, does the rating have to be at, like, let me binary search it, like the answer, and when I binary search the answer, my question is like, is the rating at does like I'm changing the question to be like, can I get a rating of at least K? And the reason you want to ask this question is because somehow when I say can I get a rating of at least K, like adding that extra parameter of like K does something to the problem. It makes it easier to work with. Like it gives you more things to work with. Like you need to you like if you're not using K, then like you're like this binary search is useless. So in some sense you must be using K because that's what you added. You added an extra parameter to the problem. So we're gonna just try binary searching it because obviously like if I can get at least 10, I can get at least 60. So obviously I can binary search this question. The question is like not exactly K, the question is like can I get at least K? That's really what we're asking. So the question, so here to know if you can get at least K, well, let's assume that like we can get at least K, and we can get at least K by choosing this interval to skip, right? Let's assume this, right? I'm just saying like let's assume that we can get it. Like, how does that look like, right? That's the question. Let's just draw it out, right? So if I can get at least K, what this is saying is I can take the first what, and then it's saying there's some interval R such that I can skip and I can get at least K. So what's that saying is that it's saying that like from contest 1 to L minus 1, if I after having some rating of like X from these contests from L minus 1, then like is this enough? Is this enough? Is this sufficient when I take contests from R plus 1 to N? In other words, is X over the minimum rating that I need when entering contest R plus 1 to finish with at least K? That's what that's what's going on, right? Is X enough when entering contest R plus 1 to finish in the end with at least K? My assumption is that it is, right? My assumption. That's the question that we're trying to ask, but this is the scenario that's going on. And we're assuming that it does work for some interval. So it's not even a question. It's like it's a statement. We're assuming that okay, it does. Let's say it does work for some interval. So it's saying that actually, it's more like saying this. It's not is enough. We're saying x is enough because I think that's a very natural, like logical train of thoughts, right? It's like saying like let's assume that if we're saying at least we're saying at least k, we want to see like does at least k work? Let's say it does work, right? This means that like I can take the first L minus one contest, have some rating of X, and I'm saying is X enough when entering contest R plus 1 to finish in the end with at least K? Seems logical to me. That's or not is X, but X is enough. Sorry, not is X, but X is enough. So yeah, gotta get this down logically clean because like again, you can read the solution, but you want to see how to like sort of motivate it. So the question is like, we first. Let me repeat this again. We first asked ourselves, can we get an answer of at least K? Okay, let's assume. How do we know if it works or not? Let's assume that it does work. If it does work, how does that look like? Well, basically, we're saying is that there's some interval LR. There exists some interval LR such that like I get an answer of at least K. Let me be more specific. When I take the first 1 to L minus 1 contest and have some rating of X, I'm saying that rating is enough when I enter when entering R plus 1 to finish in the end with at least k. So how do I know that this is enough? Well, then I say the prefix max is enough to is enough is greater than or equal to the minimum rating needed when entering R plus 1 to finish in the end with at least k. So the question is like, can we find this min rating guy? Like, is this guy findable? And it's like, well, think about this. For contest m plus 1, you know that like when entering this, you must have at least k. So the thought process is that maybe you can go backwards. Like maybe this is like some DP sort of like local thing. If you can go backwards and start just like filling out this array. So if you're going backwards, right? And so the idea is that like, can I find I knowing and I know this guy? Well, the assumption is that like you know that like min rating of I is not going to differ by min rating of I plus 1 enough, because I'm basically saying that like whatever min rating is, I'm going to compare with my a sub I to get min rating of I plus 1, to get the rating after I contest, or like before contest I plus 1. I'm going to get like whatever that rating is, I'm going to compare with a sub I and I'm going to get there. And we know a comparison can only add the value of like 1, 0, whatever. You know what I'm saying? But the problem though is that we don't actually know what min rating is. So like, how do I know like if I need to add 1 to it or like, subtract 1? So but we know that like it's not going to differ from min rating that much. So I'm first just going to assume that min rating is like just this guy. I'll assume that it's like just this guy. Like they're basically the same. And I'll see like, okay, and then I'll see like how to adjust. So if they're like the same, then I know that like if like what I compare this to is like greater than like this guy, like if my rating is like if I'm performing better than my rating, then I'm definitely saying that I'm going to add 1. And if I'm going to add 1, then I know that like this guy, if I'm going to add 1, then you can be less than me. Like I don't care if you're less than me by 1, because I'm going to add. Well, I need to because it's a minimum 1. So I say I need to subtract 1 because I know I'm going to add 1, because I have to somehow like get to um I have like when I take the I plus 1 contest, I have to make sure that the contest that I'm entering with is min rating I plus 1, like the I plus 1 one. So if I know that like this guy is greater than me, then like I can like just like remove 1, like for sure. Leave a sub I is greater than me. So similarly, it's like same thing as like this case is tricky. This case is really really tricky. So this case. So again, the assumption is like I'm assuming that like min rating is like min rating or min rating I plus 1 is min rating of I, because like you're not like from this value you're comparing it with this value to like either add 1 or 0 or not, or like it's basically the same thing, but like you just have to adjust locally on the spot. So I need to make sure that like from min rating I get there to min rating I plus 1. If I know this is true, I know that like I'm not gonna do anything. I'm not gonna do anything, and I'll be good. Like I'll still get there, but this is really really tricky, because the idea is that like if they're the same, like if min reading I is the same, like if this guy. So for example, maybe be a little bit more clear. So let's say I have like let me call min rating as like mn. So and this is got this I. Like I'm assuming like the equivalence of this, right? I'm assuming the equivalence of this. I know that like if this guy is the same, like if this guy is the same as this, like I'm gonna be like this equivalence will stay true. I'm gonna like I'll be able to get there, right? But like I know that like if this guy is like at least like one less than me, then like it will be greater. Like this will be greater than that, and I'm gonna add one, and I'll still get there. So either I can like be one less than me, and then still get to mid I plus one, or I can just be that. But since it's like the minimum rating, then I just choose this guy. So like the equal case is also minus one too. Yeah, so that's a little tricky. Like that was really tricky for me to see. But yeah, it's a little tricky. The equal case is also minus one. I guess it's just because like you assume that first you need like some basis, right? So you assume like they're the same. And when you assume that they're the same, like well, if that guy, the min I, is the same as ace of eyes, that has no effect. But you can also be like one less than me because then we'll like add one and also get there. So it is a tricky thing to see. I don't really know how to like motivate like some intermediate thoughts to get there, but like it's sort of like just like kind of just see it. You know, it's kind of annoying. DP probably is like cleaner, but because this is that notice is annoying. But then the other case is easy, right? If this is true, then you know that like you performed worse than what your assumed value is for min rating I plus one. You performed worse, so you're gonna lose 1 point. So in the point that you lose, you need to make whoops. Well, you can see that. So for the point in the point for the point that you lose, you need to make sure that like you since you know that you're gonna lose it, so it's gonna like so it's gonna bring this value down. Make sure that like you set min rating I plus one or min rating I to min rating uh I plus one since you know you're gonna lose the point. Yeah, so that's basically how you find that, and then once you find the min rating, it's really easy. Once you actually find this array, I think the trickiest part was actually finding this array, like because once you find this min rating, then it's just like, does there exist like some value that's like greater than this array? So it's like for every prefix maximum that I fix, then like I just care about the maximum about like, or I just care about the smallest one in this. So I can just like, I guess it's just like, yeah, you can. This is pretty easy though because you can just like, while you're taking like a prefix maximum, at the same time you can also run like from the back and then like just get like the minimum gut. Or actually, no, you can't do that. Oh no. Well, you just need to just like we'll just get the from the suffix like from the prefix like you have some fix and prefix and then you need like some r such that like that's true. So then obviously you want the smallest r possible. So the condition is true. So just get like the minimum suffix from there. And that obviously works. I'm sure you can like code that easier though. Because I saw they didn't put like a suffix array, but I mean, it's easy enough. Like, who cares? Yeah, who cares? But yeah, that's pretty much true. Like that's pretty much the bulk of the solution. Like in my opinion, I feel like the bulk of the solution is like thinking about like coming up with this array and then like actually finding out how to like get the array. It's like kind of tricky and it's like kind of annoying because like you just have to like sort of like do some like local adjustment on like because like you know that min rating of I is like basically min rating of I plus one. You just gotta locally adjust it, and it just depends on like the like inequalities. But that part was hard to meet for me. Like the equal case, noticing that like okay, um if I set this like the if I set like the min rating I to the min rating I plus 1, I need to like make sure that I can compare it to a sub I and get there to I plus 1. And I can be one less because I know that I'm going to add one more and I'll still get there. And that's my minimum one. I can also get there by like just being exactly the same, but I can also get there by being one less and adding more. But obviously, if if a sub I is going to be better than me, um, then I can just like do minus one, like just do minus one, then I'll still get there by adding one. And if a sub I is like more than me, or a sub I is if a sub I is less than me, or then I need to add one because I know it's gonna subtract one. So then I'm good. So yeah, it's sort of that's what it is. Sort of just assuming that like it's it's the same thing, but like you can adjust it. Yeah, pretty annoying, but yeah, let's see. It's a pretty good problem, I guess.